Good evening, everyone. Welcome to this 11th episode of the webinar series conducted by Alumni Association of the Faculty of Agriculture at University of Peradeniya. As promised during our previous event held on 29th May, we are back here again, as I told you, with an important topic, an important subject area where all of us would like to upgrade our knowledge, know about the new things that are happening on ground and what is in store for our future, especially with respect to agriculture. Before we start the program and introduce a speaker who is not new to every one of us, but then still to go ahead with a little introduction of the AAFAUP, Alumni Association of Faculty of Agriculture, University of Peradeniya, Dr. Tushara Vikramarachchi, who actually initiated this event with lots of enthusiasm. Over to you, Dr. Tushara Vikramarachchi, to address the.
Thank you. Thank you so much. It is actually our 11th webinar program of our webinar series. Actually, this is the successful 11th one. I believe that we have conveyed many the messages and knowledge to all our participants. Actually, today we are privileged to have Professor Saman Dharmakeerthi, as Udit sir called. Is not new to us. He is not new to the agriculture field, but today we are lucky to have him again with the very important matter on the fertilizer efficiency. We are going to talk. He is going to talk about the fertilizer efficiency today. But I should thank to all our participants, because their engagement is very meaningful for us to. It is very encouragement and motivation for us to arrange this type of webinars in future also. I should thank Professor Saman Dharmakeerthi, also the Professor Buddhimarambe as the moderator for all this webinar. Throughout this webinar series, actually, his involvement is very much important here. We can get the deeper knowledge with this engagement for this one. That is actually I wanted to thank today, because he's always behind us as a member, as an executive committee member also. Thank you. Then we will, then hello. Then we will get into our today's subject. Then I will hand over everything to the Professor Buddhimarambe. Thank you, sir.
Thank you very much, Dr. Vikramarachchi, and that's the president of the AAFAUP, who gave the welcome remarks to all the participants. Well, members, there's a kind request from everyone, the organizers. Please make sure that you're muting your microphones. And this webinar is not open for questions asked verbally, but you are always welcome to post your questions in the chat box, where I will have the liberty in selecting the questions, not selecting, actually posing all those questions, but depending on the time availability to the speaker, to the presenter that we have invited today as well. On 29th May, we had a very interesting webinar on biochar. A lot of people showed great interest, and there were lots of questions flowing in to understand what biochar is, what is meant by it, and what is its practical use. That's the most important part that everybody wanted to know. With that successful program today, we are skipping and we are jumping, leap jump forward again to another very interesting subject area. As Dr. Vikramarachchi said, of course, when you use fertilizers as a major input, we are worried and we are concerned, and we actually want to have a fertilizer that with higher efficiency, so that the productivity and total production of crops will be increasing, and that's the ultimate objective of having those inputs. So today we invited Dr. Saman Dharmakeerthi again to give us a talk, do a session on another interesting topic, building up from what he did last time. Of course, it's talk about the fertilizer efficiency, but the title that he has chosen is Enhanced Efficiency Fertilizers. Let's see what they mean. Well, Professor Saman Dharmakeerthi is a professor attached to Department of Soil Science of the Faculty of Agriculture, University of Peradeniya. I must also tell you one thing. The program that we conduct Usually, it's a planned program. In other words, the moderator and the presenter has a good rapport and a dialogue, understand the subject area, understand the common issues related to the subject, and we try to respond to clarify doubts, clear our minds with respect to crucial areas in terms of in terms of this knowledge sharing exercise that we do. So, as I told you, it's a programmed event, and there'll be a kind of a question answer system that goes on. And I take the privilege of asking few questions from Professor Saman Dharmakeerthi, but of course they were pre-planned questions, and Professor Saman Dharmakeerthi will be continuing it as a presentation thereafter based on different time intervals that I stop him and then ask questions. So that is the modality that we go ahead usually. And for the members who are joining, you're always welcome, as I told you earlier, to post your questions at any given time during the presentation. But those questions will be posed to Professor Mandar Mukherjee or any speaker to that effect soon after the presentation concludes. So that's a modality that we have been practicing for the past 10 webinar events, and today is the 11th successful one that we are going to have. Okay, Professor Dharmakeerthi, I think it's time to ask my first question, as we thought a lot of people will have this issue in their mind when we talk of enhanced efficiency fertilizers or EEFs. That's an important point. So, Professor Dharmakeerthi, we talk of fertilizers, now we talk of enhanced efficiency fertilizers. What do they actually mean? Why you selected EEF as a topic today? What is its importance? Would like to know from you. Over to you.
Okay, thank you, Professor Marambi. Am I audible?
Yeah, loud and clear. Go ahead.
Right, so let me start my screen sharing. Yeah, I hope you can see my...
Yes, we can see it. Can you please put it on to the presentation mode, President?
Sure, I will go ahead. Right. Okay. Right, and thank you very much for inviting me for the 11th webinar of the Alumni Association, and it is a privilege to make a presentation to this August audience. So for the second consecutive time in the webinar series. So in a way that I'm privileged and I'm humbled as well giving this webinar. So yes, Professor Maram, we were discussing about biochar and their usage and how we use them in increasing soil fertility, whether it is whether it can be used in all situations in the last time. So I thought this it is always better that we talked about, when we talk about soil fertility, one of the very valuable input nowadays is the application of fertilizers, right? So it is very important that we apply fertilizers judiciously, right? And so I think the knowledge that we have about the efficiency of fertilizers and how we should manage fertilizers is equally important when we talk about crop productivity, soil productivity, and soil fertility management, and etc. So I thought of talking about some technologies that are being linked to fertilizers and a group of fertilizers called enhanced efficiency fertilizers, so that we are very well aware about what it is and what is the terminology means and what aspects covers that. And we talked about first generation fertilizers, second generation fertilizers, third generation, and so on and so forth, depending on the at times and the technologies that we used to generate these fertilizers. Rather than going with this first generation, second generation fertilizers, I thought it's better that we use a more scientific term in grouping fertilizers, enhanced efficiency fertilizers. So we will be discussing that. And to the question that you posed, Professor Marame, when I look at a fertilizer, I define a fertilizer as any substance, any material of either natural or synthetic in origin that applies to soil. So these are materials that are that are supposed to apply to soil or to plant tissues or any plant part to supply plant nutrients. So these are the definition of fertilizers. But when we talk about FAO definition of fertilizers, they add that a fertilizer should contain collectively more than 5% of plant nutrients in it, in addition to this particular definition. So it is a suffix, and that is where we can draw the line between amendments and fertilizers. And in 2021 and 2022, when our agriculture was shifted to organic agriculture, people used to call compost also fertilizers, but in fact, they are not per se a fertilizers. So fertilizers are any material, synthetic or natural in origin, that is supposed to supply plant nutrients once applied to soil or plants. So when we more specifically define enhanced efficiency fertilizers, they are a group of fertilizers that reduces the losses to the environment and or increase nutrient availability compared to conventional fertilizers, right? They should be able to increase the availability in the soil for plant uptake and also reduces the losses to the environment. So these are the two important aspects about when we talk about enhanced efficiency fertilizers. So either one or both has to be there in enhanced efficiency fertilizers. But when we look at the literature about enhanced efficiency fertilizers, in my previous definition, the fertilizers are substances that provide plant nutrients. But in this group of enhanced efficiency fertilizers, people talk about inhibitors as well. They are not directly fertilizers or providing plant nutrients. They will go together with fertilizers added, so that they used to call them as enhanced efficiency fertilizers. For example, if you combine urea with urease inhibitors, for example, that is a enhanced efficiency fertilizer. So they have inhibitors as well in this group of enhanced efficiency fertilizers. So why we need to talk about, by the definition, it says that we need to reduce the losses to the environment and increase the availability for plant uptake, right? And when we look at the world population that is fed with synthetic fertilizers. So this data I compiled from our World in Data database, and it has a population that is fed without nitrogen fertilizers is given in blue line, right, by year 2015. And about 48% of the population, current population, is fed with the support of fertilizers, synthetic fertilizers, in this particular case with nitrogen fertilizers. So just imagine a place where we don't have nitrogen fertilizers, then almost half of the population will be subjected to hunger, and there won't be food available. to feed their stomach, right? So this is a very important thing that we need to remember, the importance of synthetic fertilizers. As you can see, this demarcation, the gradual increase was started from 1960s onwards, where we talk about green revolution and the invent of new varieties that are more responsive to fertilizers. That is in order to feed the demand of the people. Right, by 2050, we are expecting a population to be about 10 billion. So in the years to come, this population has to be fed with some fertilizers. But yes, of course, we can produce fertilizers and feed our nation. But the problem is about 40% of the applied nitrogen and almost about 90% of applied phosphorus is lost to the environment due to various processes: leaching, denitrification, volatilization, runoff, and erosion, right? So what happens to these lost fertilizers, lost nutrients, lost fertilizers? And in fact, they will have a huge influence on different environmental and health issues. For example, climate change, eutrophication or the pollution of surface water bodies, and human health issues. And of course, when the applied fertilizer is lost, about half of it is lost, then it is the profit of the farmers that will reduce, and also biodiversity. It also affects biodiversity. What is left or lost to the environment will cause all these problems in the nature, right? To quote you few examples to elaborate on this, on biodiversity, people have predicted or observed that the herbaceous plant richness has been decreased by 16% because of the lost fertilizers, and believe that about 71% of the population is exposing to overdoses of nitrates, either in water, in food, or in aerosols, right? So there can be lots of impacts on the environment and also in the health. So there's a demand, and not only that, the environmental and health effect has cost us heavily. And in a recent publication, I found that it is somewhere around, rough estimation is about US dollars 200 to 2000 billion each year, the social cost alone from these losses of fertilizers to the environment, right? Not the wastage of fertilizer per se, but the social cost involved in health costs and environmental cost and things like that, right? Which is a huge amount in monetary terms. So, in order to reduce these losses, and in 2019, I think Sri Lanka was spearheading this program to reduce nitrogen waste losses by 50% by the year 2020 through the Colombo Declaration that was initiated by United Nations Environmental Program. So we are one country that have signed this Colombo Declaration and pledged that we are going to reduce our nitrogen wastage by 50% by year 2020. Whether we can achieve that or not is a question, but we should move towards that goal if we are to survive on this planet Earth. And as a and to have a sustainable agriculture. These are some of the very important points.
Yeah, thank you very much.
Remember.
Yeah, thank you very much, Professor Dharmakeerthi. These are very useful points, and you set the stage nicely to go ahead with the continue with the presentation, responding to our queries. Once again, colleagues who have joined recently, please keep in mind this is a planned presentation. The questions are asked by the moderator and responded by the speaker today, Professor Dharmakeerthi, to ensure a sequence of issues in a scientific and a sequential order being sorted out so that we can clear our minds, get to know more about the subject, and to understand how important the subject matter that we are presenting to you today. So, Professor Dharmakeerthi, when I look at this 200 to 2,000 billion US dollars each year, social cost, I was thinking of Sri Lanka's economy. We are a $76 billion economy for last year after going through this economic recession. Even if we say that we are 100 billion, we have never reached the 100 billion mark. How many fold, how many times of Sri Lanka's economy that is considered as a social cost associated with nitrogen pollution alone in the global scale. That's an important point, important fact that we all have to keep in mind to make sure that we sort out this problem. Okay, Professor Dharmakeerthi, you're talking about EEFs, enhanced efficiency fertilizers, and you give a clear-cut definition also, and also made us aware that it's not only the fertilizer per se, even an enhancer or an inhibitor combined with the fertilizer can make the whole complex into an enhanced efficiency fertilizer. Now, the question that comes to our mind usually is that, are they available in the market? Is it a new thing, new subject area that we are talking about? I think members or participants as well as others will definitely have these questions in their minds. Over to you, Professor Dharmakeerthi, for your response.
Right. Enhanced efficiency fertilizers were not new. They were existed for about last 50 years or so, but under different names. Names like slow release fertilizers, controlled release fertilizers, stabilized fertilizers, right? But even though they were there in the market for about last 50 years or so, this is only a small fraction in the total fertilizer industry, right? And slow release fertilizers, controlled release fertilizers, and stabilized fertilizers or stabilizers, they definitely will reduce the losses to the environment, the fertilizer losses to the environment. But yet, they are only a small fraction. And just think about Sri Lankan situation. And if you go anywhere and you will say that I'm applying urea, nothing else. But if it is some slow release fertilizers, only a very small fraction to date. Why it is not popularized? The first thing is that it is high cost to make these enhanced efficiency fertilizers. There's a lot of processes going on to develop these slow release fertilizers. And most of the very effective enhanced efficiency fertilizers are made from non-biodegradable polymers to coat the fertilizer. So repeated applications of these non-biodegradable polymers will accumulate in agricultural fields and will eventually break into small pieces and can cause something like nanoplastics or microplastics, right? And that way they can pollute the environment, right? And the second and fourth points is also very important, that farmers are looking at it from a different angle. So they are not very sure about whether it's going to work in our situation or not. And to that effect, we have very limited field level testing of some of these fertilizers, right? And even in the cases of promising for EEFs or enhanced efficiency fertilizers, their results are variable under different soil crop climatic conditions. So similarly, like biofertilizers, for example, they are not performing in all environments equally, right? Therefore, there are variable responses or benefits that we will get from soil crop climatic conditions. So we need to have a very good understanding about this before we adopt these fertilizers. So these are some of the reasons why they are not popularized among the farmers, and not only in Sri Lanka, but in elsewhere in the world as well, right? But there are few EFs that are still being used. One group is called low solubility compounds. These compounds are not readily dissolved in water, but they dissolve slowly in the soil solution once we apply them into soil. So there can be organic compounds of that nature. For example, urea formaldehyde, isobutylene diurea, IBDU, and urea acetaldehyde are some of the common organic compounds that dissolve slowly once applied to the soil. The second group of low solubility compounds are inorganic compounds, like metallic ammonium phosphates, like magnesium ammonium phosphate or partially acidulated rock phosphates. And these things are inorganic in nature, but again, their solubility is very low because of the very nature of their very chemical nature of these compounds. The third in this category is encapsulated fertilizers. They are covered by synthetic polymeric matrix or sulfur or some mineral material, like let's say clay-coated urea, for example, in good old days, right? So synthetic polymeric matrix is the most common at the moment, and sulfur coating is another process. And why they are slowly soluble? Because first we need to dissolve this sulfur or break down the polymeric matrix. Then only they will start releasing or dissolving fertilizer inside it, and then releasing them into the atmosphere, right? So this is the first group of fertilizers, enhanced efficiency fertilizers, right? The second group of enhanced efficiency fertilizers, most of us are aware, there are of two kinds, and sometimes people used to call these two terms interchangeably: slow release fertilizers or controlled release fertilizers. But of course, they are slightly different from one another, right? So slow release fertilizers, they have a longer duration of the release nutrient than conventional fertilizer. They will release nutrients over a longer period of time, so that there's enough time for more time for plants to take up the nutrients in it than conventional fertilizer. But their rate, pattern, and duration of release are not well controlled, right? So once applied, the release is affected by external factors such as tillage, moisture content, pH, mechanical stresses, swelling and shrinkage, and things like that, right? So therefore, their release rates are not well controlled, but they will stay over a longer period of time than the conventional fertilizers. But on the other hand, controlled release fertilizers, the rate, pattern, and the duration of release are well controlled during the manufacturing process, and the rate of release can be simulated and controlled by external factors in the soil. So they can be stimulated and controlled by external factors. Some of these controlled release fertilizers, once you apply them into the soil, because of the moisture, they can be go into the fertilizer and start releasing the nutrients in it slowly, right? So in order to give you some explanation about these two, slow release and controlled release fertilizers, I quote from Lee et al. Right, in your left hand side, it is a slow release fertilizer and the mechanism, and to your right hand side is the controlled release fertilizer and its mechanism, right? Now let's look at this slow release fertilizer. There's a coating around the fertilizers. In this particular case is sulfur coating, and you can see this coating can be damaged due to two reasons. One is cracks due to sunlight or mechanical forces, or sometimes water can dissolve this sulfur slowly and open up some spaces, right? And from these spaces, then the nutrient will come out. The water goes in from these cracks, dissolve, and the dissolved nutrient comes out, right? So this is the nature of slow release fertilizers, and you cannot control these cracks, and the coating depletes due to dissolution of water or from microorganisms. So in the case of sulfur coating, sulfur oxidizing microorganisms can break down this sulfur coating and open up spaces. And through these small spaces, the nutrients will come out, and eventually it will break down into small pieces, right? So this is the slow release. But on the other hand, when we look at the controlled release fertilizer, you can have a good polymer coating, and the fertilizer core is inside. As you can see, polymer coat is intact, but there are certain pores or spaces through which the water can move into the polymer coating, and this water will dissolve the fertilizers, and it will build up osmotic pressure, and then due to this osmotic pressure, nutrients inside it will come out through the membrane. So the membrane is intact during the entire process, and you can easily control the release rates using the membrane, right? In nowadays, most of the coatings are polymer coatings, as I mentioned. They are non-biodegradable, and therefore they can accumulate in the soil and eventually into microplastics. There's another group of slow release fertilizers, which of course with the invent of this biochar technology only it evolved, and where the biochar matrix, because of the porous nature, if you can remember our discussion, if those who presented for the last discussion, and these fertilizers can go and bind to these functional groups on the biochar, and also physically entrapped inside these micropores, and then start releasing them slowly. And therefore, they are called biochar-based slow release fertilizers, right? And in addition to that, as I mentioned, there's a group of inhibitors that can apply together with the fertilizers in order to enhance the efficiency of the fertilizer use. These inhibitors are usually, we have nitrogen fertilizer related inhibitors. First group is called urease inhibitors. you know, urea, once you apply it to the soil, will not be taken up by plant as urea. It has to first break down into ammonia and carbon dioxide, and then the ammonia will be taken up by plants, or ammonia will be converted to nitrate, right? To convert urea into ammonia, there's an enzyme called urease present in the soil, and if you block the activity of urease by some chemicals, then they will not convert, urea will not convert to ammonia or carbon dioxide. So urea hydrolysis is inhibited, right? So there are three common urease inhibitors, and led by NBPT, N-butyl thiophosphoric triamide, and that is the most leading and most commonly used urease inhibitor to block the urea hydrolysis process. But there are phenyl phosphorodiamidate, PPD, or ammonium thiosulfate is also used in some occasions. But if you look at the urease inhibitor, this is the group of inhibitor that is most commonly used. And once ammonia is in the soil, ammonia tends to convert into nitrate through a nitrification process, which is a microbial process. And in order to block that, we can use nitrification inhibitors. And the most commonly used nitrification inhibitor in the world is 3,4-diethyl pyrazole phosphate, DMPP, is the most widely used nitrification inhibitor. But in Sri Lanka, we have seen some research conducted using dicyandiamide and also nitropyrene, right? And these are some of the inhibitors that we can incorporate into fertilizers and apply in order to enhance the efficiency of the fertilizers. So these are some of the commonly used efficiency enhanced fertilizers globally, even though we are not extensively use them in under Sri Lankan conditions.
Thank you very much, Professor Dharmakeerthi. That was very clear, the way you presented the scenario to us. Well, you said these fertilizers are not used heavily in Sri Lanka. It looks like they are promising, but they are not used. They are not being in use at a level that we expected them to be there in the situation. Is it mean, I mean, what comes to my mind always, Professor Dharmakeerthi, when I listen to these things, Sri Lanka, we always say we have very high diversity. We have 3 climatic zones, 7 agroclimatic zones, 46 agroecological regions, and you mentioned there are more than 120 soil series in this country. So when you look at that diversity and that complexity, how effective these enhanced efficiency fertilizers under Sri Lankan condition? Over to you.
Right. Yes, they are not widely used in Sri Lankan farm communities, or even in the plantation crop sector as well. I think partly this has been linked to the our previous material subsidy program that the previous government has enforced or given to farmers. They have given nitrogen, phosphorus, and potassium fertilizers free of charge to every body. So when anything is offered free, then farmers or anybody will not be bothered too much to protect their environment, and then to, of course, there are some conscious people, but they will not spend additional something to reduce the fertilizer usage and save the environment. So I think that is one of the biggest reason why it has not been sort of popularized. Now, since there's a material subsidy have been withdrawn, and the cash subsidy, the people can now think of more effective fertilizers package or enhanced efficiency fertilizers to their crop environment, provided that their profits are guaranteed. I mean, their return for the money is guaranteed, right? But as I mentioned at the very beginning, they are very expensive at the moment. So we need to work towards developing enhanced efficiency fertilizers at a lower cost. Right. But particularly during the last couple of years or so, or maybe last 3-4 years, people were more concerned about the environment and protecting the environment. I think credit should go to this organic fertilizer movement, organic agriculture movement. People were trying to sort of understand there can be some environmental impacts and health impacts related to indiscriminate use of chemical or synthetic fertilizers. And I think there's a new research component is also being evolved during the last 3-4 years or so to evaluate some of these promising enhanced efficiency fertilizers under Sri Lankan condition, but only very limited literature is available. And what I'm going to do is I will use some of these evidences and share with you to give you some idea about how effective they are under Sri Lankan condition. So I'm going to present an experiment that is carried out by Professor Nishankar. He tried to evaluate some of the fertilizer technologies that are available or that are about to promote in Sri Lankan market by the fertilizer companies. And he evaluated them for potato cultivation in Nuwara, right? So you can see some of the treatments that in that particular experiment. And so treatment 2 is the recommended urea level from the Department of Agriculture. And there are some compound fertilizers, slow release fertilizers, and also inhibitors being used. These are efficiency enhanced fertilizers that are available in the globally, but also Professor Nishankar, with the help of the fertilizer companies, trying to evaluate their effectiveness. And this is in 2023, I think Yala data, if I remember correct. And he has slow release fertilizers. DCD is the dicyan diamide, which is a nitrification inhibitor, and NBPT is a urease inhibitor. So there's a mixture of both nitrification inhibitor and the urease inhibitor together with urea fertilizer. And then some special potato mixtures by certain fertilizer companies, and some compound fertilizers, coated urea fertilizer, and then there are some other efficiency enhanced technologies that he has included in the trial. But what you can see is T2 is the only the recommended level of nitrogen as urea. And when you look at some of the products available in the market and the rates that are given, you can see the green is the yield. Potato yield has been increased in this particular site. And also, the efficiency, agronomic efficiency of these fertilizers In this particular case, he is evaluating nitrogen and nitrogen sources. The efficiency also has been increased. I think this blue line should come over here by some other, due to some reason it has gone up, but it should come here, so that the blue is the efficiency. The efficiency of the fertilizer we use available in the market appears to be, in this particular season, in Nuerelia, is promising, right? So, in terms of agronomic efficiency and the yield of the crop, right? I'm going to quote another experiment evidence. As you remember, do you remember that I talked that biochar can be used to develop a slow release fertilizer? And as you can see here, these are some of the urea encapsulated or intercalated biochar pellets. And this pellets was used at Batalagoda Research Station over 3 consecutive seasons in 2019 Yala, 2019-20 Maha, and 21. And what you can see here is you can obtain the same yield with reduced rates of nitrogen by about 25%. The same yields with reduced rates of nitrogen. And of course, therefore, the efficiency of that particular fertilizer has been increased significantly, right? Of course, the 50% slow release fertilizer is efficiency is much higher, but their yield is less. Therefore, may not be sustainable in terms of productivity of the land. But the same yields with a higher efficiency, you can use this one in this 3 situations. But again, in the same particular fertilizer was tested with some botanical inhibitors, botanical nitrification inhibitors, and urease inhibitors, plus nitrification inhibitors. And botanical inhibitor is supposed to control the nitrification process, and NBPT and DCT supposed to control both urea hydrolysis and nitrification, right? And they were applied together with urea and or the slow release fertilizers, and their yields were evaluated, right? And you can see that this is the 100% nitrogen as urea only, and yield has been slightly increased, but they were not significantly different statistically. When you look at the efficiency, application of or cutting down of nitrogen by 25% is much more efficient than the 100% nitrogen in this particular season in this site, right? But the slow release fertilizers that was tested was not, even though it is better than the current 100% recommendation, but having 70% urea only have a better efficiency than having encapsulated them in the biochar matrix or using inhibitors in this particular year. So the effectiveness of different same enhanced efficiency fertilizers vary from one season to the other and from one site to the other site as well, right? And this is the same one is used in chili under pot culture, and also for potato in Nuerelia. And you can see Professor Nishanka and Professor Varshidandaniya together with me and the others who conducted this trial. And in this particular case, in the case of pot culture, the slow release fertilizer developed using biochar was giving a very high dry weights of dry matter weight, and also apparent nitrogen recovery also significantly higher compared to the nitrogen recommended level of nitrogen as urea. In the case of potato, for example, and you will see the same yields in the potato cultivation in this season, and with only less than 25% of SRP. Therefore, the efficiency of the urea should be higher in this particular case compared to the 100% urea alone situation. So, in Norelia potato cultivations, you can obtain a higher efficiency, meaning that losses are reduced. Losses of nitrogen is reduced in this situation, right? So I will quote one more last slide. This is the another trial that has been evaluated using the biochar incorporated urea pellets and some urease inhibitors. Limus is the commercial name or the trademark, which contains NBPT and NPPT, two urease inhibitors in it. And in the current recent literature, it is found to be very effective in some environments. But of course, here 75% urea compared to 100% urea, the yield is higher and the efficiency is also higher. But with the introduction of NBPT, with or without SRU, meaning biochar intercalated urea, has not been given that particular advantage, a similar advantage as 75% of urea. So these inhibitors seems to me that they are working in some environments in Sri Lanka and not working in the other environments, right? In general, people talk about the degradation of these inhibitors under very high temperatures, particularly NBPT, and also under very acidic conditions. Their activity is going to be affected. They can be degraded very quickly into other components, other compounds, and their longevity in the soil as an effective urease inhibitor is going to be less. So, with the very limited information so far available under Sri Lankan conditions, you can see in some environments, particularly in the Norelia potato cultivation, some of these systems were effective, but in this is at Dambulla in a yellow season, where the temperature is very high in this 2024 trial, and therefore the effectiveness of these inhibitors and even these slow release fertilizers were not very evident in this particular case. So all in all, what it says is the effectiveness with very limited information available so far is vary from different location, different crops, and different seasons under Sri Lankan conditions. But we need to go for a long way ahead to understand why this happens, and therefore we need further research has to be conducted with very close scrutiny, because they have been working. Some of these effective fertilizer technologies are working in some other environments very well. So that is the situation at the moment, and I think now people should start working on these enhanced efficiency fertilizers, and conduct more research, more field work, and try to better understand their effectiveness under different soil, crop, and climatic conditions in Sri Lanka.
Thank you very much, Prof. Dharmakeerthi. Thank you for bringing in very latest information to the knowledge of the public, to let people know that although we have not used the technology, forget about the optimum use. We have not even started doing these things in most of the cases, but to let people know what is in store for us. Well, though we are late adopters usually in many of the cases, especially in relation to agriculture, the world moves on. So according to your own perception, Prof. Dharmakeerthi, what advances do you think we can expect in the future with respect to these EFF technologies? Over to you.
Right, yeah. As far as we discuss now, I think we understand that some of these technologies are working in certain environments, and in certain other cases it's not working. But some or other we need to reduce the losses of fertilizers to the environment so that we can save at least a fraction of that 200 to 2000 billion US dollars of social costs, right? So with that aim, people elsewhere in the world is moving forward in conducting research on the effective fertilizer technologies. And you remember that some of the drawbacks why they are not being adopted or effective is because they are non-biodegradable polymers. So in the next generation of EEFs, I would expect, and certain research has already been started on developing biodegradable polymers, and people are using some polysaccharides because they are very easy to find, polyphenols and polysaccharides, and polysaccharides like ketosane, starch, and arginate, and also some are using lignin as well as a biodegradable polymer to encapsulate fertilizers and to control release fertilizers. So that is one area of research that is being emerged. And the second one is the inhibitors for different soils and different climates, right? And from the very limited information that we have at the moment, we saw that the certain inhibitors are working in one environment but not on the others, right? That is, of course, the case elsewhere in the world as well. For example, if you look at NBPT, the urease inhibitor, and in acidic soils, they are degraded more, and under very hot conditions, they degrade even faster, right? And some of these inhibitors can be break down by microorganisms into their other products so that their effectiveness is reduced. Depending on the microbial community in that particular soil, their effectiveness is going to be different. So in the next generation of EEFs, we would expect that they will develop inhibitors that suits to a given particular soil climatic conditions, right? The current situation in the developing or identifying inhibitors is to check their effectiveness, check the effectiveness of the chemicals already available in the store, and they just check randomly, arbitrarily their effectiveness. But going a step beyond, what they are trying to do is now is to understand the process and understand the chemicals nature of it and where it works and where it is not working, and try to change the chemical nature of the inhibitors so that we can come up with a better inhibitor for a given soil climatic condition. So that is the type of research being carrying out now. Then the third one is they will be incorporating the nanotechnology to control release fertilizers from the matrix, and people are talking about metal phenolic networks which are hydrophobic in nature, meaning that water will not come inside the controlled release fertilizer, and because of the hydrophobic nature of this metal phenolic networks, and they are going to then coat these fertilizers in different layers using nanotechnology so that they can design the release of rate of nutrients according to the requirement of the environment. For a dry environment or frequent drying environment, you have a different set of polymers, for example, right? So metal phenolic networks is another branch of research that is being carried out and will be available in next 5-6 years time. The most interesting part is, to me, is that the development of a EEFs, efficiency enhanced fertilizers, just listening to the plant signals, right? What does it mean is that when the plant is under a nutrient stress, they will release some signals in chemical nature to the rhizosphere, and the microorganisms in the rhizosphere will sort of translate to understand these signals and then act differently, right? So I will illustrate this in a good good picture in a while, right? The first one is the natural polymers. Natural polymers like chitosan, alginate, and starch, and they are the material that is going to cover the fertilizers, and they can be used as microspheres, films, microcapsules, or hydrogels in fertilizers. And once they are applied into the soil, they absorb water and release nutrients back to the soil, and this will be degraded by the microorganisms and will increase the or enrich the soil environment with some useful carbon materials, right? So this is the type of research that is going to get evolved, and particularly the changing the structures of these chemicals using our knowledge, and will be able to effectively control the barrier to the release of nutrients by blocking the water come into the fertilizer granule, right? So that is one. This in the similar scenario. So once we have a polymer designed from organic substances, in this case lignin, and the fertilizers can be encapsulated using these lignin polymers, and either they can be break down by microorganisms and release fertilizers to the environment, or water can move in to the fertilizer granule and release nutrients in it in the case of controlled release fertilizers like artificial polymers or synthetic polymers, right? Or else you can use these organic lignin ligands and combine with cross-linking agents and build in between with fertilizers, and then they will absorb water depending on the how hydrophilic they are, and dissolve the fertilizers and release them, right? So these are some of the technologies that are going to go. But the most fascinating thing is about listening to the plant signals, right? What, as I mentioned, when the plant is under nutrient stress, they will release some signals to the rhizosphere, and in this side, plant signals are incorporated into the fertilizer coating. So these signals can be characterized and isolated, and they will be incorporated into the coating of the fertilizers, so that once you apply this fertilizers with these signals in it, and the microbial community in that area will realize that there's a stress for plant, and they will attract beneficial microorganisms and start converting previously unavailable nutrients to the plants. And the second one is these signals can be sensed by some other chemicals, and these sensors are going to incorporated into these coatings of the fertilizers, and once you apply, they can sense the plant signals and start releasing fertilizers from there accordingly, right? So this is a new branch of research, and they will call this as not as enhanced efficiency fertilizers, but they will say that it has smart fertilizers, for example. Smart fertilizers, depending on the plant requirement and the environmental conditions, they can manipulate the release rates so that you have a better synchrony between plant demand of nutrients and the supply of nutrients in terms of fertilizers. So these are some of the areas, new areas that I think will be evolving in the near future, Professor Marambe.
Right, thank you very much. That's useful information. So a lot of hope being given to us by Professor Dharmakeerthi about the futuristic developments with respect to the enhanced efficiency fertilizers. My last question to you, Professor Dharmakeerthi, today. There are a lot of questions are in the chat box, which I have to throw at you in a while. My last question to you is that cutting down and summarizing everything in a nutshell, what are your take-home messages with respect to enhanced efficiency fertilizers? Over to you.
Right. What I think, even though they have been these effective for efficient fertilizer technologies, enhanced efficiency fertilizers were existed for over last 50 years or so, their usage is very low. That is the first thing that we need to understand, because of various reasons, because of their high cost, because their effectiveness is not very apparent in different climatic conditions, and the farmer profits are going to get lost and things like that. So not all EFFs are effective in all environments, right? So we demonstrated that the effective fertilizer technologies that we have in our sleeves at the moment, their effectiveness vary from different soil crop environments. So we need to be very cautious about this fact in the future, particularly when we are educating farmers on efficiency enhanced fertilizers that are available in the Sri Lankan market. And the third one is we need to develop low cost EEF technologies that are essential for sustainable agriculture. So farmers are very worried about their profit over the environmental concerns. Nowadays, farmers are conscious about environments, but when we do a when we did this National Research Council mega grant developing environmental friendly fertilizer technologies, one of the social survey that we conducted among the stakeholders highlighted that yes, we are very concerned about the environmental aspects, but it has to be cost effective, right? Whatever the technology for Sri Lankan farmers at least, right? Because they do, even though you are very conscious about the environment, and our farmers' situation is very poor, and therefore we need to come up with low cost technologies. And whatever the available technologies, we need to test them under field conditions, under different environmental conditions. And I think Department of Agriculture and other crop research institutes, as well as the university academia who conduct research on these areas, have to come forward and evaluate what are available in the Sri Lankan market, and whether we can reduce the fertilizer usage in the country, so, and also at the same time protect the environment. And I think one of the way that I think in terms of policy decisions, what we can do is, I think even though it is not directly evident to our farmers or community, the social costs of lost fertilizers is going to be huge. Globally, it is 200 to 2000 billion, but even under Sri Lankan conditions, it could be a very sizable social cost. Some or other government has to bear that cost. Whether we can transform some part of that social costs that the government is bearing in terms of subsidies in order to promote these effective fertilizer technologies, may be something that we can think of in developing policies for the agriculture sector in the future. With that, I think we conclude the presentation, and thank you very much. And I'm hoping to answer any questions if you may have at the moment.
Thank you very much, Professor Dharmakeerthi. Well, colleagues, that concludes the presentation, and there are a lot of questions already in the chat box, so I will stop receiving questions now because of the time constraint, and I will ask the questions on behalf of the audience that and also behalf of the people who have posted the questions in the chat box. Well, Professor Dharmakeerthi, the first few questions come from Dr. Jayat Kirthasinghe, who was one of our former members at the Academy of the Department of Crop Science here at the Faculty of Agriculture at Peradeniya. The first question, maybe going a little bit beyond your field of study, but interesting. The question is, are there any plant genes related to absorption of nutrients?
Yes, of course, it is beyond my expertise, but I know this. I think the crop science department, Professor Surya Goda, have conducted some trials, and also at the moment I think the Batalgoda and also Batalgoda Research Station also conducting some trials, that there are varieties that are less responsive to added fertilizers, and there are responsive to fertilizer added. So that response comes from, I think, genetic makeup, I guess, from the plants. So therefore, there should be some genetical genes that are involved in uptaking plant nutrients, definitely. And under poor environmental conditions, to absorb more fertilizers, more nutrients, and under high environmental conditions, high nutrient conditions, to absorb whatever, but translate it into higher yields. So definitely there are genes available in the plants, but whether people have tried to translate these genes or incorporate these genes into different plants, I think uh, some research have been conducted, particularly in the Japanese, uh, in Japanese research. They have isolated some of these genes and tried to incorporate into different different varieties of rice to enhance the uptake efficiency of the fertilizers. So, but under Sri Lankan conditions, what I know is that we have identified different varieties that are less responsive and more responsive to added fertilizers, giving higher yields. And also a similar that is for phosphorus, and also there's a branch of research is currently being conducted for nitrogen responses as well.
Yeah, thank you, Prof. Dharmakeerthi. To add to what Prof. Dharmakeerthi said, there are about 6 genes that have been identified as transporters, nutrient transporters within the plants to enhance the nutrient uptake as well. There are genes for ammonium transportation, nitrate transportation, and phosphorus in plants. So those have been linked to absorption as well. And there's another gene that have been identified, Prof. Dharmakeerthi, to uptake copper from soil. Uh, which gene was identified from eucalyptus plants. So that's a very kind of a miraculous thing. We know when copper toxicity there in soils, nothing can be done, right? We thought the land should be just either field or cities being built up on such a land, but there are some hope coming up now with these new technologies being and new scientific breakthroughs being identified. So thank you very much. The next question is also from Dr. Keerthi Singha. The question is, I mean, you're talking about this coated fertilizers. His question is, why use sulfur to coat fertilizer? Over to you.
Okay. So the coating, when it started in the very early days, is used to control the release of fertilizers. So when you have a sulfur in the coating, it has to be break or dissolve or break down in somehow or other. For example, if you look at clay coating, for example, a fertilizer, it has to be break down only by mechanical stresses. There's no other way, a practical way to break down this coating so that the fertilizer inside it taken up. But when you use sulfur, there are two things is happening. One is to coat sulfur, and during that period, there was a branch of research evolving very widely that people have identified sulfur deficient soils, and therefore one aspect of it is to provide sulfur with nitrogen. The second aspect of it is the most using it as a coating material, and sulfur can be dissolved, or sulfur coating can be break down through microbial activity in the soil, and it is a slow process. Therefore, the breakdown is also going to be slower, and therefore the material inside will release slowly. And that microbial process is sulfur oxidation. A group of microorganisms called thioxidants, they will degrade or convert elemental sulfur into sulfur dioxide, and by doing so, they will break or make holes in that sulfur coating, so that because of it being a slow process, the material inside will release slowly through those small pores that has been opened up.
Okay, thank you very much. Roshan Perra asked a question based on, remember, Prof. Dharmakeerthi, you said that about 40% of the nitrogen and 90% of the phosphorus that we apply are lost to the environment. So the question from Roshan is, while there are many EEFs for urea or nitrogen, are there any EEFs available for phosphorus? That's the question.
Yes, yes. Yes, traditionally, most of the concentration of developing slow release fertilizers is because nitrogen is a very mobile element and it can be lost very quickly and particularly leaching down. And also there are so many other pathways to get it lost from the soil. And that is why a huge amount of literature or products are available to control the losses of nitrogen. But when it comes to phosphorus, there's a phosphorus, even though it is not goes out from the agricultural field as leaching losses or volatilization, but there can be some runoff losses and also erosion losses of phosphorus fertilizers once they adsorb to clay particles in the soil or iron and aluminum oxides, right? And recently, there's another branch of research is evolving because of the phosphorus pollution of surface water bodies. Therefore, added phosphorus has to be retained in the soil, or a small amount of phosphorus has to be added so that the phosphorus uptake by plant is synchronized with phosphorus release rather than applying them all together as we do it as a basal dressing at the moment, right? So therefore, new research is also coming, and there are articles that are dealt with combining phosphoric acid and triple superphosphate with biochar matrix so that the release of phosphorus is slowed down so that the plant can have more time to take up the release phosphorus. So yes, there's phosphorus, slow release phosphorus fertilizers are being developed at the moment in the world market, even though they are still at research stage, but they are not commercially available at the moment, I think.
Thank you very much. The next question is from Professor Mapa. Well, I think maybe a member from the Department of Agriculture can also assist in responding this, if not now, later. The question is, if a private company wants to import EEFs, do they have to get permission from the Department of Agriculture? And what is the time taken to get those approvals?
As far as I am aware, any fertilizer to be imported into the country has to be the approval has to be taken from the Fertilizer Secretariat. So they have to, any company who wants to import a efficiency enhanced fertilizer generally have to make a request to the Fertilizer Secretariat and get their approval. When it is the request come to Fertilizer Secretariat, and if it is something, if the facts are not enough for them to grant approval or not to grant approval, they will get the idea or the advice of the Fertilizer Advisory Committee, and they will assist the director NSF to what to do with these fertilizers. Then they will issue approval to import fertilizers. So that is how it happens. It is the Fertilizer Advisory Committee is headed by Act is the Director General of Agriculture. So I think that is the process that has to be adopted at the moment.
Yeah, I mean, I don't think just a hybrid fertilizer or anything can be brought into Sri Lanka unless there's experiments being done and recommendations being given. That's a process, as Professor Dharmakeerthi said. But of course, in an experimental level, there will be a chance to bring in material with the approval of the Department of Agriculture as well as through the Fertilizer Secretariat. to be tested in Sri Lanka. So the commercialization can take place later. And that process will take place, of course, at least 1 season or 2 seasons of test depending on the crop that we use it. Thank you very much, Professor Dharmakeerthi. There's a question from Rajita Viduranga. The question is, can the phosphorus fixation in soils be reduced by using slow-releasing fertilizers? That's the question. If so, how does it work? Over to you.
Right. Now, phosphorus fertilizers usually comes as either monocalcium phosphates or phosphoric acids. And to fix them into the soil, first it has to come to its ionic form, and then only it will react with iron, aluminum, or manganese, or whatever the other things, or even calcium, to fix into the soil as aluminum iron phosphates or calcium phosphates. So whatever the fertilizer that is available is not readily fixed. First, it has to dissolve and come to a orthophosphate or transform into orthophosphate, that is monohydrogen phosphate, dihydrogen phosphate, or phosphates. So if you can slow down this conversion of phosphorus fertilizer to orthophosphate ions, then the chances of fixing them in the soil matrix is also reduced. So what the slow release fertilizers does is, they will slow down the release rates of these fertilizers to soil solution, and in the soil solution only they will break down into orthophosphates. So once the process is slowed down, and also the eventuality is that the fixing is also reduced.
Okay, right. Thank you very much for that. This is the last question that I'm going to ask you, President Dharmakeerthi, based on the audience, the questions that have been posted, again from Roshan Perra. The question is that, why do we control nitrification if ammonification has already been carried out by ureas? Over to you.
Right. Urea is converted to ammonia, which is called urea hydrolysis, not ammonification. So once it is converted to ammonia, there are several pathways for ammonia, or the fates of ammonia, taken up by plants, evolved it as ammonium gas, or fixed them in the clay matrix as ammonium ions. And a part is available for soil microorganisms, particularly nitrification microorganisms, nitrosomonas and nitrobacter, to convert them into nitrates. So that is the nitrification organisms, microorganisms are present in all soils. So naturally they will utilize the ammonia in the soil solution and convert them into nitrate. Once it is converted to nitrate, nitrate can have several other pathways, which is relatively very quick process under Sri Lankan or tropical conditions. And ammonia will be converted to nitrate within 2-3 days time, right? So urea will hydrolyze and convert to ammonia within 2-7 days, usually within 2-3 days. And that converted ammonia can also be converted to nitrates very quickly. Once ammonia nitrate is converted, nitrate has several pathways, can be taken up by plant, which is what we need, but it can be leached down and pollute the groundwater, and it can be denitrified and go back to nitrous oxides to the atmosphere, which is a greenhouse gas. So we do not want to pollute our groundwater or pollute our environment or the air. Therefore, we need to reduce the conversion of ammonia to nitrate. That is why we apply nitrification inhibitors.
Well, thank you very much. And thank you very much, the audience, for asking interesting questions, where Prof. Dharmakeerthi has provided interesting responses as well. Scientific background with all due recognitions of science, and keeping in mind that we are trying to clear people's doubts. And that's an important part in the development of science as well. And that's one of the major objectives of the AAFAUP, the webinar series that it conducts. We are now concluding the session for today, and we are looking forward to meeting you again in 2 weeks' time with a similar interesting subject and another interesting and of course, well-recognized resource person on board. Thank you very much for everyone who are joining us. Have a good night. Thank you.
Thank you very much, and good night to you.